Okay, cool. Let's start. So we all know that current language model, large language model, and vision language model, they are super powerful. So based on the paradigm of next token prediction, and also the new architecture about transformer, you can train a super strong large language model and vision language model. So basically, here I present the left figure. So for the pre-training process, the idea is like usually you will have some unlabeled textual crops, and you have a model. Usually this is a transformer, and the objective function is next token prediction loss. And by combining these three components, you can train some really powerful large language model, and it can lead to, we have Cloud from Anthropic, we have Gemini from Google DeepMind, we have GPT-4 from OpenAI. But they still have a lot of weakness. So basically, current large language model, they cannot reliably criticize itself and to self-judge itself. So basically, there's some recent paper that says the large language model cannot self-correct yet. And also large language model still struggles with tasks that requires long-term planning. So there's another paper that tries to benchmark its performance on some planning and reasoning tasks. And also large language model have several hallucination problems. I guess that's something we all know, that it makes a lot of mistakes, especially for domains that it has never been trained on. And also I share a Twitter from Ian LeCun that he says, autoregressive large language model cannot plan and cannot really reason. So given this weakness, is there any potential path that might lead to the next generation of large language model that can somehow address some of these issues? So let's introduce like reinforcement learning. So here's a brief recap. So basically, the reinforcement learning objective is trying to model the long-term cumulative reward. So assuming you are an agent in an environment, so shown in the left figure, typically we model the decision-making process as a Markov decision process. So imagine you are an agent and you are inside an environment. You are trying to do something that can interact with the environment and optimize your reward function. So the procedure is like, firstly, the environment gives you a state ST, and you're taking the state, you as an agent taking the state, which you generate an action AT, and the AT will be fed into the environment. So the environment can change because of your inputs. It will gives you the next state, ST+1, and the immediate reward RT+1 to your agent. So it's a iterative process until your episode ends. The objective of reinforcement learning is just trying to optimize for the policy so it can maximize the cumulative discounted reward. So since this is a cumulative reward, so it's inherently try to model the long-term effects. And in reinforcement learning, there are 4 key components. So the first one is dynamic model. So basically, it's like a what-if questions, something like if you are given the state ST and if you are taking the action AT, what's your next state? So that corresponds to the dynamic model. So basically, it's in traditional reinforcement learning, it's modeled as a statistical model. So you are trying to predict the probability distribution over the next state, given current state and current action. And the second component is policy. So it corresponds to a mapping from the current state to your current action you are going to take. So similar with dynamic model, this is usually a statistical distribution over the candidate action in action space. The third component is the reward function. So it corresponds to the immediate reward term, like how will I be rewarded if I'm taking the action A given the current state S. And the value function. So the value function is kind of like similar with reinforcement learning objective, but it can start at any given state. So for the objective, basically it's tries to model the long-term cumulative reward starting from the initial state, but for value function, it's start from any given state. So basically, what is my cumulative reward if I'm taking the action according to current policy and starting with the current state as t. So that's the value function. And basically, these four components are key components in our reinforcement learning. Okay, that's the reinforcement learning introduction. So how does RL influence our current large language model and vision language model? So of course, first from the algorithms level, we have reinforcement learning from human feedback. So basically, from the context of reinforcement learning, it tries to identify the reward function by implicitly by human preference. And I'm sharing two papers. So basically, these two papers are like fundamental papers for reinforcement learning algorithms, RLHF algorithms for large language model. The first one is like the first paper that proposed RLHF stuff, and second one is the OpenAI's paper that tries to use the RLHF to train the large language model. And we all know that it leads to GPT 3.5 and more GPT model from OpenAI. And also from RL algorithms parts, it can be used for scenarios if you have a reliable reward signal. So it contrasts to RLHF, since in RLHF you have to use human preference to implicitly identify the reward signal. But what if you have a reliable reward signal? So that leads to RL algorithms, RL for mathematics, RL for code, RL for reasoning, because in most cases, these domains can be verified. Like for example, in mathematics, basically you typically have a ground truth for math problems. So you can identify whether the model's output, the final answers, it corresponds to that ground truth. Or you can have something like a programming language. For example, in mathematics, you have math. You can do math, verifiable math, using something called link. And it's the same for code. Like for code, you can execute code. You can try to see if there are any error message, and also you can have some test cases to make sure the code works as you're instructed to do. So for all of these domains, they have a relatively reliable reward signal, and it leads to achievement from Google DeepMind that they have alpha proof, and they leveraged all alpha theory algorithms and combined with the link I just mentioned, and it can finally achieve silver medal level player in international mathematics Olympic problems, and also OpenAI 01 with large-scale reinforcement learning training and test time scaling. And we all know that, like yesterday, OpenAI also announced like the full version of 01. So that's how reinforcement algorithms is influencing the mathematics, code, and reasoning tasks. And the two parts I just mentioned are from algorithm level. So what about the concept level? So from our concept, we have something we call the word model, and it's super hard nowadays. So the word model, in fact, it corresponds to the dynamic function in the reinforcement learning context. So basically, what's your next state, given the current state and current action, what's your probability distribution? And the word models comes from the paper from Jürgen Schmidt-Huber. But the concept can trace back to like the end of 20th century, but I assume this paper to be the most famous one recently. And basically in that paper, they somehow train a model that can predict the next frame given the current frame and your player's action. For example, the first one is the racing car, and the second one is some shooting games. Basically, what is your image next frame if you are giving some commands to the computer. And you can see that at that time, the performance is still not good, and the image is quite vague, and I'm pretty sure that that's not the word model we imagine. So it leads to the word model we have now, especially I would say this year is a boom for word model development. Basically, we have Sora that can create video from text, And yesterday, like 2 days ago, we have Jenny 2 from Google DeepMind, the large-scale foundation word model that allows you to input commands from computer, like from mouse, from keyboards, and can create new words, like a gaming words, in diverse scenarios. And also we have large language model agents. That's also from the reinforcement learning concept. Because the term agent is widely used in reinforcement learning, such as, for example, reinforcement learning agents. That's how we typically code our reinforcement learning policy in traditional reinforcement learning. So it in fact corresponds to the policy. So the probability of your action given your current state. So I just use a red box to note what agent refers to. And also now we have research from Google DeepMind that tries to use the language model agent to interact with the real website. So maybe it can serve as an assistant to you to complete some of your tasks in the near future. And also we have Cloud 3.5, Sonat for computer use from Entropy, that you can also use the large language model to control your computer to do a lot of tasks. Okay, given those recap, here we are going to somehow a conclusion or a vision, like what reinforcement learning can bring to the next generation of large language model. But I also summarize stuff in 2 levels, so at the algorithm level and the concept level. So conceptually, we're hoping that the large language model can have all the reinforcement learning components. So remember, I mentioned that there are 4 key components in reinforcement learning, and for sure, we are hoping that the next generation of large language model can have all of them. So the first one is the accurate word model. So basically, it can accurately model how future state evolves given the current state and the current action. And second thing is the policy, especially policy with long-term planning and reasoning ability. So we all know that reinforcement learning is well known because it beats the professional player in Go in the game of Go. So we also hope that our large language model can have such policy with long-term planning and reasoning ability. And third one is the evaluation. So basically the value function and the reward function. So it can somehow self-correct based on that evaluation from the feedback of value model or reward model. So the last 2 things basically corresponds to the AlphaZero training part. In AlphaZero, you have policy and you have a value. So we are hoping that we can replicate the success of AlphaZero with long-term planning ability and reliable value model for evaluation. And what's more, they should go beyond traditional reinforcement learning because they are doing things in natural language space, so they are more interpretable and more generalizable. And from algorithm level, so how reinforcement learning algorithms can help large language model inference and training. And the number 1 reason why we adopt reinforcement learning algorithms is that it can generate superhuman and or synthetic data. So we all know that we are running out of high quality data. I mean, even the website is really large source of data, but we are still running out of it. And reinforcement learning is the only machine learning framework that can generate synthetic data and superhuman data. So I show in the Go board. So this moves 37. So basically, this is the board from the game between AlphaGo and Sodali. And AlphaGo makes this surprising move 37 at this board. So basically, at that time, no professional player believed it's the correct move. But after analyzing this move, they found that it's reasonable and it's probably the optimal at this situation. So given this, basically we can see AlphaGo somehow proved the boundary of human intuition and try to generate some superhuman data in the game of board. And for sure, we hope that we can replicate the success of this move 37 in more generalizable domain and in natural language space. And also the second reason could be look-ahead training. So basically, we're trying to model long-term effects. So that's the concept of reinforcement learning, because we are trying to optimize the cumulative reward, not just like immediate one. So we are hoping that reinforcement learning can help the large language model to become something beyond just simple next one token prediction, because either value or policy, they all consider long-term effects. So if we have large language model with strong value or policy, then it's definitely means that it can model something in a long-term circumstance. And also we have some research that tells us the next token prediction has some pitfall, and we might need to solve them with some techniques like reinforcement learning. Okay, so that's some conclusion and vision, and let's go into some details. So basically, these are some of my PhD work about the vision I just mentioned about. So the first one is ChessGPT. Basically, we build a chess agent with all of the reinforcement learning ability I just mentioned. So basically, modeling ability, policy ability, and value function ability. And the second one is AlphaZero, like tree search can guide large language model with decoding and training. So basically, it's correspond to how we hope that reinforcement learning algorithms can introduce some look-ahead training and to help with the large language model reasoning ability, planning ability during inference and during training. And the final one is like my recent work. It's called natural language reinforcement learning, and it's about how we can use reinforcement learning algorithms to generate some synthetic data in natural language space. And they can generate synthetic natural language data for both language critique and language policy. Let's start the first one. The motivation of ChessGPT is that we believe typically when human do decision-making process, they typically rely on two sources of data. The first one is historical policy data. For example, in the game of chess, that corresponds to some chess game replay. So I show an example in the left figure. So this is a replay example in portable game notation. So it's called PGN. So PGN is a game notation defined by chess player. So they use this format to represent the game. So if I record something like the players, the elo rating, the final result, and some other meta information. And also, for sure, the most important is the gameplay, how the game works. So that corresponds to chess game play. And second thing is the analytical insights and strategical thinking process, especially something that can be expressed in natural language form. So the right figure is an example. So this is a screenshot I took from some chess player blog. So basically, they will try to annotate some given board using some natural language description. So basically, that means that it can make a bridge between the modality of the chessboard and the modality of language, and they're usually pair data. So from this motivation, it brings our ChessGPT paper, and basically we present ChessGPT, a GPT and CLIP model that tries to bridge the policy learning and language modeling part by integrating data from these two sources in chess game. And so this paper is a data set and benchmark paper. So we offer a full pipeline about a large chess data set and the model trained over the data set and a full evaluation process over the model we train. So firstly, the data set, we include data from different sources, including game data sets. So basically the game record from some online game, from some professional player games, from chess puzzle, from computer games, or from some modeling games. So the modeling game just means that something like, if I'm at this board, if I take this move, what's your next board? So we are hoping that such tasks can help the language model to understand how the board works, what's the rule of the board. And the second data set is the language data set. So they are basically free-form language we take from the website, including some general text about chess, including Wikipedia about chess, books about chess, and blogs about chess and forum about chess. So they are free-form language, but they are all about chess. And third data is the mixed data, and I would say this is the data set like with the highest quality. So all of data set in this section is pair data between the modality of chess and the modality of language. So for example, there are some data set we call it annotated game. So basically that corresponds to pair data between a chessboard and a corresponding natural language description, something I showed as an example here. And we have collect some data set from internet about annotated game, and also we create some synthetic data, pair data from YouTube video. So the idea is just we treat the frame and the transcript at the same timestamp as some aligned data, and we extract it from the image to get some chessboard, and under that we have pair data between the transcript and between the board we extract from the image. So we can create some synthetic pair data between these two modalities. And final data is the conversational data set. So basically that's correspond to things like the first three data set. They are somehow pre-training data set, and the final one we need something to instruction tuning. So it can generate some human-like conversation, just like how we interact with ChatGPT stuff. And we collect some instruction tuning data set from GPT-4, and also we build some conversation based on the discussion over the Reddit about some chess. And building upon data, we create basically three models: ChessGPT base, ChessGPT chat, and ChessClip. So for the first two, so basically they are trained over. So for ChessGPT base, it's trained over the first three data sets, so it can benefit from policy based on training over the first and the third data set, because they are all game related, and also they can benefit from language learning by training it over free-form language and mixed data set. So that's how ChessGPT base is trained. And further, we fine-tune our ChessGPT base using the instruction tuning data from GPT-4 and from Reddit forum. So it can give the model the chat ability, and the generation are more interpretable. So that's ChessGPT base and chat. For ChessClip, we mainly utilize our third data set, so basically the pair data set. So we build a clip model that consists of like two encoder. One is the text encoder that can encode text. The other one is the board and action encoder. That's where we are using AlphaZero way of representation to generate some embedding for that, and we are using the contrastive learning to optimize it, so it can somehow learn a text encoder and the board and action encoder that can be aligned based on the correspondence between these two modalities. So here are some qualitative results. So basically, it's small, but basically we are prompting our model with something like a PGN. So basically this is a chessboard, and we ask it to generate some annotation step by step. And we found some interesting samples that our chat model is capable of analyzing the game similar with how human annotate a given chessboard. And there are some chess concepts produced by the model that is correctly corresponds to the chessboard. So basically we believe that our chess model can at least somehow grasp the understanding of chess, but for sure it can also create some hallucination, just like other language models. And this is the qualitative result for our ChessClip. So basically, this is the similarity matrix between the text description and the board, and the diagonal represent the corresponding text and board. So basically, the lighter the color is, the higher the similarity is. So we show that our model indeed generates the similarity matrix with the lightest grade in the diagonal. So which means that our ChessClip model can accurately capture the relationship between language-based chess term. So for example, the chess description, they are somehow chess opening names. and AlphaZero encoding in chat state and action space. And for evaluation, we evaluate its modeling ability. So something like what's your next state, or what's your next 5 state given the current state and some of the action. And value judgment ability, something like I will give you a board, and can you help me evaluate the board game? And policy evaluation, for sure, it's just like how we evaluate our chess policy. We just let it play the game and to see the performance. And basically, since our model is trained over chess-specific data set, our ChessGPT base and ChessGPT chat can basically smash all other comparing large language model in like different tasks. Okay, that's the first paper. And the second paper is about tree search enhanced large language model. And the motivation for this paper is that from the success of ChatGPT, we know that we can somehow formulate a large language model generation problem as a Markov decision process and optimize it with reinforcement learning algorithms. And the reinforcement learning is well known because of AlphaZero's like success. And it shows that you can have AlphaZero that can effectively using tree search algorithms in large-scale Markov decision process, such as Atari, chess, and Go. And we all know that natural language space is definitely a large-scale Markov decision process because of its like really large action space and state space. So the idea is that can we combine these things together? Can we combine large language model with AlphaZero? So basically, instead of directly predicting the next token, the large language model maybe they need to generate its answer by conducting deep tree search for the most valuable words or sentence. And that leads to our AlphaZero-like tree search paper. So we proved that it's possible to incorporate AlphaZero into large language model encoding and training process for solving a diverse range of tasks, including reasoning, planning, and RHF tasks. So here's the pipeline. So basically, this is an iterative process between inference and training. So during the inference, we're treating the generation program as a tree. And so, for example, we present 2 ways of node expansion. For example, you can represent each sentence as a tree node or each token as a tree node. So there are different representation way, and they have their pros and cons. And building over these trees, we typically will have a policy network powered by a large language model and a value network powered by large language model. Then we run AlphaZero like tree search algorithms over the large language model policy and the large language model critical function to get some improved trajectory for the next iteration of large language model training. So the green part just corresponds to the training part. Like you have the improved trajectory from the AlphaZero process, and it's easy that you can just try to distill the policy and distill the policy evaluation by using something like supervised fine-tuning process and taking regression over the value function. So for example, for the value learning, basically for reading tasks, you can have some correct answer, you can have some wrong answers. So you just learn a value function using the large language model decoder as the backbone, and just to regress like what's the likelihood of these reasoning paths to be correct or not correct, something like that. And after training this, it can be replugged into the AlphaZero's tree search process. And so this is an iterative process. You can keep improve stuff. And here's the results. Basically, we test our learn framework on several reasoning and planning language tasks. I present 2 takeaway here. So basically, the large language model's evaluation ability is really bad. If you just prompt it, it's not reliable. So we test something like we're using the same tree search algorithms, but with different evaluator. So one evaluator is from like directly prompting it. So basically, you prompt the large language model and ask it to directly evaluate if a given reasoning is correct or not, and we are using that as a signal, or we use the AlphaZero ways of value function training. So we were training a network, and we compare the performance, and basically, in all domains that the trained value function are all like much better than the prompting GPT 3.5, which means that our LLM might not be that great at evaluation. We still need to do something like AlphaZero value function training. And the takeaway too is that so basically we try different baseline search algorithms, and we try AlphaZero, and we didn't find that AlphaZero can benefit the large language model decoding process in all domains, and we only find it's useful if this is a relatively long planning problems. For example, in our RLHF task and in chess endgame task. So the reason RLHF is a long planning task is because we are using token as node formulation for RLHF. So, for example, assuming that you have a sentence that's with like 100 token, that means that you have a depth equals to 100 search tree. So that's a relatively long search tree and long planning problems. And it can only get a comparable performance on shallow search one. So we tested on some other games. So relatively, they only have shallow search depths, like on something under 10. So basically, it's somehow the AlphaZero's tree search is basically similar with other search tree. So which indicates that maybe AlphaZero is not the cure for everything, unless you have a really long planning and search problems. So that's the second paper. And the final one is natural language reinforcement learning. So this is my recent work, and I just posted it to arXiv a week ago. So the motivation starts from ChessGPT. Yeah, we at that time we were trying to develop like our second version of ChessGPT, but we are facing challenge because if you want to scale the large language model, there are basically two ways. Either you scale your data, or you scale your model. And for sure, in academia, it's hard for us to scale model. So the only thing we can do is try to scale the data, but it's really hard because we basically have tried to scrap every data from the internet, but the quality is really mixed because you never know that. For example, for a given chess annotation, you don't know if it comes from a grandmaster or it just comes from a beginner. So there's no way for you to figure it out unless you have some other chess expert to annotate it. But it's pretty expensive and it's completely not scalable. So is there any other ways that can let us try to scale the data for ChessGPT without any human effort? So, and then we find two observations. The first one is the AlphaZero critic function. So we all know there's a value function in AlphaZero that can guide the tree search process. And it is definitely super strong because by searching using the MCTS, it can produce like superhuman policy, which means that they are definitely super strong. And since it's a value function, for sure, they can be seen as the board annotator and evaluator. So it can somehow provide you feedback like which side takes advantage at this given board. But there's an issue. We cannot directly utilize the AlphaZero's critic function because usually this is just a one-dimensional scala. So basically it's just like +1, which means that maybe y takes advantage, and or -1, which means that maybe black takes one, but no other information can be provided to you. And it causes a problem that sometimes even for professional players, it's really hard for them to understand why AlphaZero is making that move. So that's the first observation. The second observation is that, how do we human learn and play the game? I mean, even for Grandmaster, it still learns by playing the game rather than by letting others directly teaching him everything. So how do humans learn and understand the game? So they do it by playing it. So for example, when humans try to evaluate the board, they do something called temporal difference learning. So temporal difference learning is something in the reinforcement learning concept. Basically, the idea is like, for example, given a board here, typically we do not directly evaluate the board because sometimes the board might be complex. There are a lot of possibility. So it's maybe really hard for us to directly evaluate the board given the current situation. So what happens here is, even for Grandmaster, they usually will try to expand the current board. So basically, they take some rollouts starting from the current board to some few variations to the future, and they will try to evaluate the outcome of these futures because the more variation, the more step you take in your variation, the closer you are to your final winning stage. So it's easier for you to evaluate the game. And by trying to trying to evaluate each variation, it can gives you an understanding of the current board. So here I show an example. For example, there's maybe one variation starting from the board, and you can use natural language description for this variation, and you can try to evaluate the future states, like after you apply this variation. And by combining the natural language description of this variation, like what's happening inside this variation, and what is going to happen after this variation. So this corresponds to the evaluation of the end state of this variation. By combining these two information, you can have your evaluation of the current states. And that's how, even for Grandmaster, that's how they evaluate and understand the game. So given this, it leads to our idea that we mentioned that AlphaZero security function is strong, and it can be learned unsupervisedly by interacting with the game. So what if we learn a language value function? So it's something like, instead of using Scala as the representation of the evaluation, we are using a language description. So something like, it's not like +1 for board. It's more like you are in the advantage because of something, because you are going to checkmate, because you are going to, there is a nice trick that can get your king out to escape from the current being checkmate, something like that. So that can be more informative. And that's exactly correspond to our need for ChessGPT. We want to scale our data. And what if we learn a language value function, and it can help us to scale data? And since we have language value function that represents traditional Scala value function in the language space, and what if we take one step further and try to verbalize all reinforcement learning components? So that corresponds to our natural language reinforcement learning paper. And we're trying to reframe all reinforcement learning concept in natural language representation space. That includes policy, value function, Bayerman equation, Monte Carlo estimation, temporal difference learning, policy improvement operate all of these reinforcement learning components into their natural language equivalents. So here is a plot for an example. For example, typically in traditional reinforcement learning, you have policy. That is typically a statistic model. So it can give you a distribution like there's 50% you can choose action A, there's 50% you can choose action B. But for length policy, it can generate something like, we call it sort. So we call it chain of sort inspired policy. So basically, instead of directly giving the policy distribution, it can somehow explain to you why he's making this move, because he believes something is going to happen. And so basically the reason for the action. And similarly, in traditional reinforcement learning, we have Scala reward, -1, +1, something like that. But in natural language reinforcement learning, maybe it's not that explicit. And maybe it can be a language feedback. For example, it can be something like, okay, your task is a goal reaching task, and you finally reach the goal. That's the final sparse reward. And for states, that's something similar. Usually we use Scala, we use some high dimensional embedding for the state representation, and maybe we can use the language states. So maybe something like you are at the cross, you are at the corner, something like that. So that's some example. And similarly, you can extend the value function of extend the definition of value function or Bayerman equation into natural language reinforcement learning. So for example, in value function, traditional value function tries to model the cumulative reward, and you can do it in natural language space. The difference is that you are using a language description to describe what's your cumulative reward is. Something like what is going to happen given your current state, and what's your final outcome. But all things represented in natural language space, and also Bayes equation. So the value function in traditional reinforcement learning satisfies Bayes equation. So basically, it's something like given the current state S, there might be some variation, and there's an equation, we call it Bayes equation, so that can model the relationship between Vs and the next state Vs primes. So there's Bayes equation here. Similarly, we can have something called language Bayes equation. So basically, conceptually, it can be seen as a consistency between adjacent states. So basically, the state S and your next state, their evaluation couldn't be too different because you are next to each other. So that's the basic concept, and also Monte Carlo and TD learning. Here I show two plots for how traditional reinforcement learning corresponds to our new natural language reinforcement learning components. So the figure, first one is Monte Carlo estimate. So basically, it's trying to use Monte Carlo sampling to estimate the value function. And typically, in traditional reinforcement learning, we use just Monte Carlo. So basically, you take some rollouts, you calculate the cumulative reward, and you take average over it. And for sure, there's no way we take average in natural language space. So we assume there's something called language aggregator. So it can somehow take the description of all your future possible variation and try to compress them into something like language evaluation, given these future variations. And something like TD learning, temporal difference estimation. In traditional reinforcement learning, we have the Bayes equation that leads to our TD learning. So empirically, we use it's still like the average over some possible, say, one-step variation, and we are calculating the current state value based on the future state's value and the immediate reward. So it's something similar. We are trying to map in the, like, say, average operation, the sum operation, and something like discount factor into their natural language space. So we assume we have a G1 for aggregating results from multiple one-step samples. We have G2 that can aggregate intermediate changes and future evaluation. Okay, that's basically the concept, but how are we going to like implement things? So for sure, they are language so for sure, we are using large language model to implement all this stuff. So I'm using the tic-tac-toe as example. So tic-tac-toe is a board game that there are two players, you play in turns, and the goal is that you have three pieces in line, either horizontally, vertically, or diagonally. So you can use large language model as the language policy. So you give a query, you ask, what's your next move? Given the current board, what's your next best move? And it gives you a response with sort and action. Similarly, you can use large language model as a language value function approximation. So basically, given the current board and the next action is that maybe 2, what's your assessment of this state action? It also gives you a sort process inspired evaluation. And also we have large language model as language Monte Carlo or language temporal difference operator. So I show 2 examples here. So for language Monte Carlo, it's you start some Monte Carlo sampling from the given current state, you roll out till the end, and you are transferred all of them into some text representation. You are asking a language model. So I give you this trajectory. Please help me aggregate the trajectory and using the future's trajectory to evaluate the current game. So it's similar for temporal difference learning. The only difference is that in temporal difference learning, you don't need to like roll out to the end. You may only need to like roll out for a few steps, and you are using the end state of these different variations. So the only thing is that in Monte Carlo estimate, you roll out to the end, so there's always like a final reward signal here. But in temporal difference operator, maybe you need another large language model to somehow help you annotate the final state of this variation, and you just input their evaluation and also this few step variation. And again, you ask the large language model to aggregate the result and generate the response. So that's for large language Monte Carlo and temporal difference. And also we can have language policy improvement. So basically, given the current board, there might be, for example, 3 candidate action, and you can give each action's evaluation results based on our language value function approximator, and you're asking, okay, I give you 3 candidate action, and here is the evaluation for each candidate action. What's your best move given this evaluation, these moves, and what's your best move to achieve your goal? So it also can give you some thought process and also define the policy improvement action it choose. And for 1 to 5, they are all there's no training, there's basically prompting. And for sure, we summarize that you can also distill your language value function estimate and improved language policy into your network. So it's just similar with how iterative reinforcement learning works. You can improve your policy, you can improve your value, and you do this Monte Carlo sampling temporal difference again, you further improve your policy and further improve your value. So that's how reinforcement learning works. So basically this diagram shows an example of how to do reinforcement learning, but in natural language space. So here we show some experiments. The first one is a language generalized policy iteration with pure prompting. So basically here we don't have any training. Yeah, we tested on maze game. So the figure 3 is an example of the maze game that you put your agent in some random position and you ask it to reach the goal. And we purely prompt GPT-4 meaning. And so we compare different baseline, including language policy, which means that we directly prompt GPT-4 to give the action, and language value function plus improvement operator, which means that we prompt the GPT-4 mini and ask it, I give you a few action candidates. Please help me annotate each candidate and do an improvement. So basically, you consider the evaluation of each action candidate, and you finally summarize which action is the best. That corresponds to language value function plus policy improvement. And third one, and the final one is the full version of language generalized policy iteration. Basically, we include the language temporal difference learning with different variational number, with different look-ahead steps. So basically, you can see from the result that is that language temporal difference learning is necessary to help the language value function and also the final performance of the policy. Basically, you can see that with more variation, with more look-ahead steps, your performance just increases. And second experiment is on language value function training with a language temporal difference learning. So basically, that's a proof of concept experiment since we don't have that much computing resource to do it on chess. So this is just like a simplified version of chess. And this is called breakthrough game. The goal of the player is to break through others' line and reach the home row of the opponent. So we are trying to use the language temporal difference learning to learn a language value function and to use it to serve as a game annotator. And we have tested different settings. So basically, the takeaway is that it can largely improve the advantageous side prediction accuracy. So that's our evaluation task. So basically, we are asking our large language model to annotate which side takes advantage. And by taking language temporal difference training, we can improve the accuracy from 0.6 to 0.86. So it's a huge jump. And we also do a lot of ablation study to verify what's important in this. And here's a qualitative results. Basically, we compare the results before the training and after the training for the same states. And there are some analysis in the paper, and the conclusion is that the language value function can accurately evaluate this board position and generate the insight for annotation, and largely decreasing the hallucination problems. And final experiment is the full natural language actor critic algorithm. So basically, we train language policy and language critic simultaneously. We test it on tic-tac-toe game, and the pros is the main result of this natural language actor critic. So basically, it can stably improve the performance compared with all the baseline in all different opponent situation, and it somehow even beat the traditional proximal policy optimization. So that's the traditional reinforcement learning algorithm, but we somehow can also beat them in this case. So that's basically all of my talk. So here's the summarization. So we believe that the next generation of large language models should be closely related with reinforcement learning for new capability in modeling, evaluating, and playing, and also the reinforcement learning algorithms for large language model training and inference process. And also I list some future important topics like how we can replicate the success of arbitrary in language domain. For example, we use the large language model with reinforcement learning to, for example, solve some open question in math, maybe. So in that step, in that direction, AlphaProof and O1, they are just initial steps. And also maybe we can consider generative model for decision making. So basically how we can use the large language model to help the reinforcement learning process. And something like large scale reinforcement learning pre-training. So just like what ChessGPT does, we're hoping that we can have expert level domain agents. For example, in chess, it can behave like a professional player at both the decision making, so both at the playing perspective and the explaining perspective. It's just like a tutor for you in chess. But we hope that we can use large language model to achieve it. So that's all. Thank you guys for listening.